So far, we have identified users and items to their corresponding row or column respectively. For example, for us, Frank was only a partially filled row of movie ratings. Frank is so much more than this row, but what really matters is what the recommendation system knows about him. Since we live in the era of big data, trust me, the system knows a lot. Given more data, it seems natural that one would just want to increase prediction accuracy, right? In the Netflix example, if we just had more user movie ratings, then one would simply be able to build a recommendation algorithm for Netflix using the same user item-based recommendation techniques that we have developed previously. What if the extra data does not consist of rating, but still contains relevant information? It should still be able to help. The main guiding principle to use such additional information is to refine our model. Indeed, just like we started with a completely homogeneous and admittedly dull model that assumed that every user movie pair was giving the same rating, all the way to the more refined user item-based recommendation algorithm, we can refine this model even further. The idea is to use site information to first group users and items into more homogeneous groups, and then work on each group separately. To illustrate this point, consider the following diagram. We start with a large pool of users and a large pool of movies. Then we use sat information to group or cluster homogeneous users into, say, 3 groups and homogeneous movies into, say, 4 groups. Then, on each pair of groups, we perform a user item-based recommendation as we've learned how to do. That's using only pass rating. So what kind of information is available? One thing for sure is that it should be relevant to our clustering purposes, which is to say that it should have enough information to discriminate users and items according to preferences, at least partially. In this sense, not all data is created equal, and it makes sense to keep in mind that when deciding which data to collect for this purpose. In practice, however, we collect as much data as possible and apply a variable selection or dimension reduction technique to keep the relevant information. Take, for example, the Amazon recommendation system. What does it know about Frank? Well, it knows not only products that he purchased, but also what product is looked at. In particular, the dance-related items. For how long he's read reviews, how much money he spends on weekends, etc. Overall, by now, Amazon has probably figured out that Frank is into dancing, what his income is, and whether he is a compulsive buyer. Frank is probably not the only Amazon customer with these features, and Amazon may be able to identify users that are similar to Frank with respect to these features. The same is true for items. Amazon knows a lot about items beyond their ratings: price, category, weight, color, etc. This is the information used to cluster items. Let us take a closer look at how clustering can be done. There are many clustering techniques available out there, but all of them start from one simple idea. Represent the objects to be clustered by a vector, this is just an ordered list of numbers, and then measure the similarity using inner products. We've done this in this very module when the vectors were the rows or columns of ratings, completing with the average rating 3 when entries were missing. When we have site information, we can create a new vector. For example, we can summarize the site information about Frank in the vector f equals 1, 0, 1, 24, 152, etc. Which means, for example, that Frank had looked at gardening equipment, the first number 1, has not looked at cooking books, the number 0, has looked at movies, the second number 1, has spent 24 minutes browsing through dance equipment, spent $152 on this last purchase, etc. Amazon may even have convinced Frank to subscribe to their credit card and even know his buying pattern outside of the Amazon website. At the end of the day, the vector f that contains the site information that Amazon has collected about Frank is gigantic, with hundreds of thousands of entries, and some are more relevant than others. Let's say that one of these entries, for example, is that Frank has purchased a flight to Vegas with his Amazon credit card. Is this relevant or not? We could sit here and debate about this question from a socioeconomic point of view, but we might as well let the data speak. There are many ways to select variable in a data-driven fashion, with the ultimate goal to get a better clustering. Some of them are covered in other modules of this course, but to name a few, we could use spectral clustering, where the goal is to find a projection of the data before clustering, sparse methods, where the goal is to simply keep only the most relevant site information, locality-sensitive hashing, which is part of the broader family of approximate nearest neighbors. Most of these methods are coded in standard software, but a few tweaks may be needed to adapt them to your specific purposes. To conclude, let us note that the clustering described above is a bit of a blunt tool and often needs arbitrary decisions. What if we have a continuum of users? How do we decide when to stop putting users in the first cluster and start putting them in the second one? Rather than making this ad hoc choice, we can simply weigh users. We put more weights on users that are more similar to a given user. There are many ways to incorporate weights into recommendation systems, but here is a rather simple one to fix ideas. Recall that in absence of site information, we computed similarity between users by looking at inner products between their rows of ratings, and that we can do the same with their vectors of site information, perhaps after variable selection. This gives us two inner products that we call IPR for inner product between ratings and IPS for inner product between site information. We can now combine the two by looking at a new hybrid similarity measure defined by IPR plus T times IPS. Here, the parameter T is positive and represents how much weight we want to put on the site information. For small t, the similarity measure essentially disregards site information, and for larger and larger t, it takes more and more site information into account. Choosing t is more of an art than a science. The best choice of t will depend on how good your site information is and should be done in light of data. Interestingly, there is another interpretation of this hybrid similarity measure. This is the measure we get if for each user, we concatenate the row of ratings with the vector of site information, where each coordinate is multiplied by the factor square root of t. It is easy to see that when we take the inner product between the two longer rows, we recover the hybrid similarity measure. We can also use different values of t for different users and choose this value from site information itself. We can use more complicated combinations. The hybrid measure that we've just defined is said to be linear. It is a linear combination of IPR and IPS. We could instead use nonlinear functions, and this is what we do when we cluster first and then recommend. In this case, the rule to compute a hybrid similarity measure is as follows. If IPS is larger than a threshold, then use IPR as a measure of similarity. If IPS is smaller than a threshold, then use 0 as a measure of similarity. The role of t here is replaced by the threshold, which has to be chosen in a data-driven way too. To summarize, we have seen that recommendation systems often have site information about users and items available. This information can be used to refine our model, that is, remove some homogeneity assumptions. Practically, this is done by incorporating site information when computing similarity between users or between items.